not on. How limited interaction hinders real communication. And this is joint work with Jakob Nordström and Mark Vigneault. So this talk will be about proof complexity. The setup here is we have an unsatisfiable formula in conjunctive normal form, and our task is to certify unsatisfiability. And these certificates, they are proof of unsatisfiability of the formula, or refutations of the formula. So we'll be using proof and refutation interchangeably in the talk. Okay, so we can think of a proof of a refutation of the formula as presented on the blackboard. So we start with an empty blackboard. Our goal is that at the end of the proof, we have proven contradiction, and we're allowed to do one of three things at every step. We can write down a clause of the formula we're refuting. We can infer a new line from what we already have on the blackboard. And we can erase lines we don't currently need in order to save space on the blackboard. And the exact details of how this is done will depend on the proof system, and we'll get to this in a minute. But regardless of the proof system, there are two complexity measures we can define. So we can define the length of the proof, which is the number of steps. And we can define the space of the proof, which is the maximum number of lines I have on the blackboard at any moment. So the proof system we're interested in is cutting planes. And here clauses are interpreted as linear inequalities. We interpret 0 as false and 1 as true. So if we have a clause like x or y are not said, we translate this to x plus y minus z greater or equal than 0. Then we have a set of rules that tell us how we can manipulate these inequalities. So we have addition, scalar multiplication, division, and our goal is to derive 0 greater or equal than 1. Okay. So don't worry too much if you haven't memorized these rules. It will not be important for the rest of this talk. What's important for us in this work is that we're operating with linear inequalities. So that's all we have to know for now. Okay, so we're interested in studying trade-offs between length and space. And we say a formula has a length-space trade-off if it has a short refutation. It also has a refutation in small space. But as soon as you try to optimize one of the measures, the other one blows up. So strong trade-offs are known for other proof systems, such as resolution and polynomial calculus, which I haven't defined, but they won't be important for this talk. So we'll be talking about cutting planes, which is a much less well-understood proof system. And so first, let's see what was known for cutting planes. And Nordström and Gospitazzi proved that there are formulas that have short refutations, and any small space refutation requires large length. But the question remains if there was any small space refutation. And actually, well, some people conjecture that this was not the case for cutting planes, because in other proof systems, these formulas did not have small space refutation. So it was a very surprising result when recently it was proven that cutting planes can actually refute any formula with at most 5 lines in memory at every time. And plugging this into the previous results, we do get trade-offs. But these are trade-offs of sorts, because the coefficients here of these small space proofs, they are exponentially large numbers. And to say that a proof is constant space when you have exponentially large coefficients doesn't seem quite right. So a question that arises is, what about truly space-efficient trade-offs? Are there trade-offs where the space-efficient cutting planes refutation has small coefficients? So in this work, we proved that, yes, such trade-offs do exist. So there are formulas that have small length refutations with constant size coefficients. They also have small space refutations with constant size coefficients. And any proof, even with arbitrarily large coefficients, if we try to optimize one measure, the other one blows up. As a byproduct of the techniques we developed to prove this, we were also able to prove an exponential separation in the monotone AC hierarchy. So this improves on the superpolynomial separation that follows from Raz-McKenzie. But for the rest of the talk, I'm going to focus on the proof complexity result. So let's see an outline of the proof. This will be a proof by contradiction through a long chain of reductions. And we start by assuming that a certain formula F has a refutation in short length and short space simultaneously. From there, we get a very efficient communication protocol for the clause search problem on this formula, which I'll define in a minute. Then we'll get a parallel decision tree for this problem. Finally, we'll get a very good diamond-Tompa strategy. And then we will have to argue that such strategies do not exist. So in this talk, we'll be able to talk a little bit about the first 2 points. So let's look at the first point. So this, if we're given an unsatisfiable formula over variables x and y, Alice receives an assignment to the x variables, Bob receives an assignment to the y variables, and their task is to communicate to find a falsified clause. So this is the falsified clause search problem. And what was shown in previous papers is that if you have a cutting planes refutation, then you can get a protocol for this search problem with randomized communication, space times log of the length of the proof. So, okay, here we make 2 simple but crucial observations, which are we do not need to use randomized communication. We can use another model, which I'll define soon, which is real communication. And the other major observation, which is very important for this work, is that the protocol we get is round efficient. So it has only log L rounds. Okay, so real communication, we have Alice and Bob, and they communicate via referee. They send some real numbers to the referee, and the referee answers with the result of the comparison of these numbers. We only charge for the bits sent by the referee. Okay, and so here we have 2 complexity measures that we care about. So the cost of a protocol is the total number of comparisons, and the number of rounds of the protocol is the number of alternations between players and the referee. Okay, so actually real communication can simulate deterministic communication. So if Alice wants to send a message to Bob, then she can send that message, and Bob will just send a vector of a halves. And it's also strictly stronger than deterministic communication because they can solve equality with only 2 comparisons. Okay, so now let's see the proof of the first point. So we have a refutation of a formula. Alice receives assignments to x variables, Bob receives assignments to y variables, and they want to find a falsified clause. So they know that the first blackboard will evaluate to true because it's empty, and the last one that contains contradiction obviously evaluates to false. So they can do a binary search here, evaluating each blackboard, and find a transition from true to false. So what happened in this transition? Well, it couldn't be an erasure. It also cannot be that they inferred something, because if they had a true blackboard, anything they infer from that is also true. So it must be that they wrote down a clause of the original formula. And I claim that that clause is falsified by their assignment, and it's the answer to the search problem. Okay, so if this refutation had length L, then they would have to evaluate log L blackboards. Then if they are able to spend 1 round per blackboard evaluation, then this gives log L rounds. And finally, if they can evaluate each line of the proof at unit cost, this gives a total cost of S log L. And real communication can do exactly this for a cutting plane. Because if you want to evaluate an inequality, Alice can evaluate her part of the inequality, Bob evaluates his part, and then they just send it to the referee to compare. Okay, so that finishes with the first point. So if we're given a formula in length L and space S, we can get a communication protocol for the search problem in log L rounds and communication S log L. So now let's see about the second point from a communication protocol. How do we get a parallel decision tree? So for that, we'll have to define the Liftina function. So here we're given a function over n bits. And we will give some variables to Alice, some variables to Bob. So Alice gets indices, Bob gets vector of bits, and Alice's indices points to which of Bob's bits should be plugged into the formula. And this is how the lift is defined. Then we can encode this lifted search problem as a new CNF formula. Okay, the other concepts we need to define are parallel decision trees. So here nodes are labeled by sets of variables, and edges are labeled by assignments. And if we have, for every assignment, that defines a path in this tree. And the leaf of that path is labeled with the answer of the decision tree to that input. And here we have 2 complexity measures. We have a number of queries, which is the maximum number of queries along any path. And we also have the depth of the tree, which is the length of the longest path. And how this relates to the lifted problem is, well, it's a nice observation that if you have a decision tree, you can build a communication problem that solves the lifted problem. So let's see an example of this. So here we have a decision tree. Alice receives indices, Bob receives this vector of bits, and they can simply follow the decision tree. So they start at the root. Alice tells Bob which index he is the input he should plug into that tree. So then Bob tells Alice what that input is, and they just follow the tree. And again, Alice tells Bob what are the indices that he should plug into the tree. And so they can continue this until they reach a leaf and answer according to what the decision tree answers on this input. Okay, so this is a nice observation, and our main technical contribution is that actually the opposite is also true. So this is essentially the best that Alice and Bob can do. If there is a R-round real communication protocol in call C solving the lift problem, then there is a depth R parallel decision tree solving the original problem in about C queries. And note that the size of the lift we need to prove this is actually polynomial on the size of the input. So in this example, the size of the lift was 2, but we're using a very large lift, which is polynomial on the size of the input. And this builds on Raz Mackenzie and Gospitasi Watson, and also on Bonnet, Seven, Galesi, and Johansson. So let's see a little bit more about the simulation theorem. So Razmatkin, Spitasi-Watson proved a similar theorem for deterministic communication. And I'll just have time to give some ideas of their proof. So the decision tree is built node by node. And it simulates the communication protocol, simulates messages being sent between Alice and Bob, and measures the information revealed by the protocol on the lifted variable. And as soon as there's too much information revealed, then it queries the corresponding original variable. So the idea here is that the decision tree cannot risk that the communication protocol figures out the value of an original variable before it has queried it. So as soon as there's too much information, it queries this variable. So here we made two contributions. So one is to make this simulation round preserving. And I'll just mention the challenge we have here is that during one round, the protocol can reveal a lot of information about certain variables. And we cannot query variables as soon as information is high. We have to wait until the end of the round because we want to do this in a round preserving manner. So this is an extra challenge. And the other one is that we extend this to real communication. And here in this model, we do not have combinatorial or rectangle properties. So this makes it harder to prove lower bounds. So this is what I'll have time to say about the second point. So from a communication protocol in log L rounds and communication S log L, we get a parallel decision tree, depth log L, and S log L queries. From there, we can get a strategy for this diamond compa game, which this was proved by Chan, and also in log L rounds and using S log L pebbles. And finally, in order to argue that such strategies do not exist, we construct graphs with trade-offs between rounds and number of pebbles. Okay, so finally, to wrap up, we proved strong length-based trade-offs for cutting planes. We also obtained an exponential separation in the monotone AC hierarchy. And the main technical contribution was this simulation theorem for real communication, taking rounds into account. And there are many interesting open problems. One would be, can we prove a more efficient simulation? So if you remember, I said that the lift we needed was polynomial on the size of the input. So can we do this for smaller lifts, even maybe constant size lifts? Also, can we prove similar simulation theorems for a stronger model of communication? And finally, if we can prove stronger lower bounds for cutting planes. So that's it. Thank you. Yes, yes. So actually, we're not taking into account exactly what the rules are. So if we're working with inequalities and we're sound, it applies. Yes.
And so the second one, does it apply for super linear space maps? So like n squared space maps versus n cubed or things like that?
No, I believe not. Space is at most linear. Yes.
Questions? Let's thank Susanna again.